Start the board. Resume the board. Okay.
You stop and start. No? It's there. Yes, Sushan. So we can start.
Yeah.
Okay. Yeah.
You can use
Yeah. So good morning, everyone, and welcome to our session today. Today, we are really happy to have with us Sushan Konar, and Sushan Konar is going to be our guide for radio data, since that's not our expertise. And we're going to have 4 very interesting sessions from Sushan. That is all the Saturdays of September, starting from today, and we really look forward to this session by the sessions by Sushan. Sushan is at the National Center for Radio Astrophysics, and we'll start off. And she's an expert at pulsars, and we hope. I'm sure you will enjoy all the sessions we're going to have with Sushan today. And you can post your questions if you wish on the chat window, but it's up to her then when to take it at the end of the session or during, right? So I welcome you, Sushan, and let's start.
Yeah. Thank you, Priya. Let me start by saying that it's an honor and a privilege to be part of this activity. And I'm sorry, I'm trying to get my presentation on screen. Yeah.
It's fine.
It's a privilege to be part of this activity and connecting up with so many people at the same time. And this is my sort of, I should say, this is my first love, Neutron Stars. So it's always a pleasant experience to be able to talk about neutron stars. And so I have never given a neutron star talk from the point of archival data mining. So this is also a new experience for me. And I hope that you would enjoy this experience and share the experience with me. And at any point of time, if there are questions and problems, I'd be very happy to address those questions. So let us begin, because it is a project on archival data astronomy. So let us first define what we mean by archival data. Usually, astronomical data is taken by telescopes maintained by various observatories, where an investigator or a team of investigators proposes a problem that they want to study, and appropriately data is taken so that that particular study can be undertaken. Now, it is the policy of every observatory that after a certain amount of time, it could range from 3 months to a year, or sometimes 2 years, whatever, depending on the nature of the observatory and the nature of the study, that data is made public. By public, I mean that the data which was taken at the behest of the proposers, they have exclusive rights till that time, 3 months, 6 months, or whatever. And after that, this data is becomes the property of the observatory, and this is made available to anybody who wants to look at these data and do further investigations, whichever is available with that study. Now, for this particular set of lectures, we would take this definition of data a little further. We would use archival data in its general sense, which basically says archival data can be thought of as any sort of information previously collected by others, amenable to systematic study. So this is not only data directly coming from an astronomical observatory, but any sort of information which could be conclusions arrived at by previous researchers. Now, let me also take a few minutes to explain what theoretical astrophysics is all about. I am a theoretical astrophysicist, so I would like to explain that for a minute. Now, astrophysics is not a fundamental science in the sense that we are not engaged in finding the fundamental physics rules of the nature. What we're trying to do here is take those fundamental physics rules, for example, the rules of quantum mechanics, the rules of classical mechanics, rules of statistical mechanics, and apply them to understand the astrophysical systems, astrophysical objects. So the task of a theoretical astrophysicist is to look at available data which has and available conclusions that other researchers have arrived at, and try to understand the overall behavior of a given system, try to model the future behavior of such systems. Now, what I do is look at the data. Of course, theoreticians in astrophysics of necessity have to look at data, because we are not going by the fundamental principles, but looking at the data that is available for a particular system that a person is interested in, and then try to understand its behavior, and then try to model its future behavior. So that's what we will do in this set of lectures. And so this is about neutron stars. Now, I may be biased, but I think neutron stars is one of the most exciting objects that one can study, because it allows you to stretch our understanding of physics to real extremes. Material is in neutron stars under conditions which cannot be duplicated in terrestrial laboratories. So therefore, we really do not understand how material behave under such conditions. So on the one hand, understanding a neutron star stretches the physics principles that we have available from our terrestrial laboratories. And on the other hand, it also allows us to understand various processes, various extreme processes. We will talk about that in a little while. Various extreme processes that takes place in the universe. So now this first lecture, we would talk about the discovery of neutron stars, the extreme physics. We would just touch upon the nature of the extreme physics. Then, of course, we would talk about radio pulsars. Now, there are about 3,000 neutron stars which have been discovered so far, and more than 2,500 of them have been discovered as radio pulsars. Now, I'll explain what a radio pulsar is. And therefore, most of the understanding about the neutron stars have come from radio pulsar studies. So therefore, that is what we must understand in little detail. And then after that, we would end today by giving you an example of a theoretical problem that we can approach using archival data. So this is about timing a null, and nulling, the phenomenon of nulling. I'll explain it later. It has been one of the long-standing problems that we have not yet understood very well in the context of radio pulsars. And I will give you one small example to illustrate how we can define such problems using archival data, and how we can try to find an answer to such a problem. So let's begin. The discovery of neutron stars. Now, the discovery of neutron stars is a very interesting story in itself. So this was February 1931. Landau, from the basic principles of physics, the basic principles of white dwarf. White dwarfs are stars which are supported. The gravitational pressure is supported by the degeneracy pressure of the electrons of the material. So from the basic physics principles, Landau derived this quantity, which is the maximum mass of such an object. So you see that we only have some universal constants that is relate to quantum mechanics, that is H cross, and gravitation, which is G, and there is C. So from basic physics principles, he obtained the maximum mass of a, at that point of time, he called it a existence of a giant atomic nuclei like star. All right. Now, you have to remember this is February 1931, and we still do not know about neutrons. So this paper was submitted in January 1932. There is a long story why he took 1 year to submit the paper. In any case, he submits this paper to a physics journal of the erstwhile Soviet Union. And what happens? Within a month, Chadwick submits his neutron discovery paper to Nature. So this comes, the neutron discovery comes later than Landau's paper. The work of Landau, the paper was published a little later. 27th February, Chadwick's paper is published, and 29th February, Landau's paper is published. So some people have this belief that the neutrons were discovered and immediately Landau hit upon the idea of neutron stars. That is not true. Landau's work predates discovery of neutrons. Now, we cut to 1933 and we go across the oceans to US, and there Walter Budde and Fritz Zwicky, in a meeting of the APS, say this: supernovae represent the transition from ordinary stars into neutron stars. Neutrons have already been discovered, so people have some idea of neutron stars, which in their final stages consist of closely packed neutrons. Such a star may possess a very small radius and an extremely high density. The gravitational packing energy in a cold neutron star may far exceed the ordinary nuclear packing fractions. A neutron star would therefore represent the most stable configuration of matter as such. So they are saying that when supernova explosion happens, the energy goes out, and this is the binding energy of a neutron star, which is more tightly packed than an ordinary nucleus. So now, in 1934, the abstract of this talk is published. Please remember, they were talking about the energy from the energy estimate of supernova, which was, they were talking about the optical luminosity of the supernova, and which is about 10 to the power 51 arc. Now, from this estimate, they found the radius of sorry, a neutron star a little off from the real values, because the maximum amount of energy from supernova goes away in neutrinos, and neutrinos were not even known about at that point of time. So the total energy, order of magnitude energy of a supernova of type 2, from which neutron stars are obtained, is about 10 to the power 53 arc, and which is exactly equal to the binding energy of a neutron star. So that energy goes out because the central region of the star collapses into a neutron star, and that's the binding energy which comes out at the energy of the supernova. So this is the concept of the neutron stars, which is happening in 1930s. So Landau's paper in 1932, Budde and Zwicky, 3 papers in 1934. And this entire story was dug up and written up by these four people, Yakovlev, Hensel, Baim, and Pethick, who are stalwarts of neutron star physics. And this is very interesting story to read. Now, as an aside, at the same time as Landau was working on finding the maximum mass from first principles, Chandrasekhar, Subramaniam Chandrasekhar, at that point of time, just finished his BSc and going over to England for his further studies, works out the maximum mass of white dwarfs, which we now know as Chandrasekhar mass. So all this interesting stuff was happening in the early 30s. Then what happens? We have to wait for about 35 years till this happens. In 1965, Anthony Hewish and Samuel Luque in Cambridge observed an unusual source of high radio brightness temperature. I'll explain what brightness temperature is. An unusual source of high radio brightness temperature in the Crab Nebula. Now we know there is this famous pulsar in the Crab Nebula called Xray Pulsar that was detected 3 years later. But this is the first time this is something very unusual. Now comes 1967, Jocelyn Bell, then a PhD student with Anthony Hewish, the same Anthony Hewish that we talked about in the previous slide, detect regular radio pulses from an object they named CP1990. This is later found to be the first pulsar with a period of 1.33 seconds. You can see this is the first chart recorder observation of the signals coming from this pulsar, and you will see this this recorder shows this chart is upside down. So here are the pulses. You see regular pulses coming at an interval of 1.33 seconds, and this is considered to be the first observation of a neutron star as a radio pulsar. Why a radio pulsar? Because we are getting periodic pulses from this object. That's why they are called pulsars, and this is in radio, so therefore this is called a radio pulsar. Now the fact that these are neutron stars, to understand that, it took people quite a bit of time and effort to identify this object with a neutron star. We'll talk about how this identification happened. So almost about 35 years before the actual observation of a neutron star was made, people already knew about the concept of neutron stars from simple physics understanding. So that is very important in the context of neutron stars. So now in 1971, a few years later, Giacconi et al. Discovered X-ray pulsations from Centaurus X3, and this is the first detection of an X-ray pulsar. Now this is a slightly different beast compared to the previous one that we talked about. This is in a binary system. It has a companion, a massive companion. So this is a high mass X-ray binary, and the physics is slightly different. We'll talk about it in one of the later lectures. But this is the first X-ray pulsars. Incidentally, both this discovery and the discovery of a radio pulsar both brought Nobel Prizes to the respective people. There are various controversies related to the first Nobel Prize in pulsars, but let's not go into that today. So the interpretation, these pulses that we are seeing from the sky, regular radio pulses, how do we know that these have something to do with exotic objects called neutron stars? In 1964, this is again before the actual observation of a neutron star, Low Volcher from simple magnetic flux conservation. If a large star goes supernova and finally collapses into a small object like a neutron star. So looking at the magnetic fields of the stars, our star also, our own star, sun also has a magnetic field. We all know about it. Now, larger stars have slightly larger magnetic fields. So if at the time of collapse, the magnetic flux is conserved. From simple flux conservation estimates, we get the magnetic field of a neutron star should be in the range of 10 to the power 14 to 10 to the power 16 Gauss. Later, in 1967-68, Franco Pacini. Now, Franco Pacini was also located in Cambridge, and actually sitting in an office a few years down the corridor from Anthony Hewish, and he did not know of Hewish's work. Hewish did not know of Pacini's work, and Pacini indicated the likelihood of strong radiation from rotating magnetized neutron stars, and he said which may power supernova remnants like Crab Nebula. And of course, the Xray Pulsar came on the scene a few years later. In 1968-69, Thomas Gold develops a similar model, similar to Pacini's, to explain radiation from CP1919, that's the first pulsar. Finally, in 1969, Radhakrishnan of Raman Research Institute, and Cook, Gunn and Oestreicher, Goldreich and Julio, they developed the basic radio pulsar model. And we must say that the basic radio pulsar model is what has been serving us till now. And there have been many modifications, many additions, but that is the basic model of Radhakrishnan, Gunn and Oestreicher, Goldreich and Julian, which gives us an understanding of how a neutron star acts like a radio pulsar. So before we go into how it acts like a radio pulsar, let us get into the extreme physics that is associated with neutron stars. Now, let us consider all the compact objects in this universe. We can start from pebbles, and then there's all these misshapen asteroids. And from there, you have small spherical objects like the satellites, the moons of the planets, minor planet like Pluto, and then bigger planets like Mars and Earth, and etc. So these are all very small objects. And of course, there is a separation between small objects like misshapen asteroids and spherical objects like minor planets. So, and there is a beautiful physics which separates these two. But from there, we come to giant planets like the Jupiter. Now, the Jupiter, the gas giants, are very different from terrestrial planets like the Earth because there the physics is different. So, giant planets with masses, gas giant planets with masses less than 13 times the mass of the Jupiter, these are objects where no fusion reaction has happened. So 13 times the mass of the Jupiter is the limit of the compact object mass in the universe where no fusion reaction happens. Now, above that, what do we have? We have brown dwarf. Now, brown dwarfs are not stars, of course, because why they are not stars? Because the fusion reaction starts, hydrogen gets converted into deuterium, but it does not go all the way up to producing helium. Now, objects which can make helium starting from hydrogen, those are the objects we call stars. So brown dwarfs, they only go up to deuterium and end there. The mass limit is from 13 to 80 times the mass of the Jupiter. Now, we have stars, and we have, after the stars burn their fuel, the convert hydrogen into helium. Sometimes later on, if the mass is adequate, from helium it will go to carbon, oxygen, and etc. and etc. So in the end, when they complete all their fuel, they go into what we call compact stars. These are actually stellar remnants, the uh, the final phases of the stars. And we have three objects: white dwarfs, neutron stars, and black holes. They come from stars of different masses. So the lowest mass objects will go into white dwarfs, the intermediate objects will go become neutron stars, and very massive objects would go into black holes. Now, there is this series of articles that I wrote in 2017 in Resonance. It is a popular level article amenable to people who have done the undergraduate studies in physics. And there I have discussed this transition from giant planets to neutron stars and black holes. If you wish, you can take a look at that. So now, a star in its active phase fuses, that is, converts an element to a higher element through nuclear fusion. So from hydrogen, it goes to helium, then to beryllium, to carbon, and so on. Now, here is a plot. Many of you may be familiar with that. It's a plot of the baryonic energy per nucleon, the binding energy per nucleon, and versus the mass number. And you see that iron, Fe56, it has the minimum binding energy. So, which means that if you try to combine iron nuclei to obtain something which has more mass, you would not obtain energy, but you have to give energy for that reaction to happen. So that's what we see, that the reactions become endothermic here. That means it requires energy, and therefore such a process would not happen in nature, because in nature, who would provide the energy? So the stellar fusion stops at iron 56, and when that happens, the star really completes, that is, finishes its stellar fuel, and the fusion reactions stops. So therefore, when the reactions stop, now for different masses, the reaction may stop at different phases. All stars, particularly low mass stars, would not go up to iron. They would stop much before that, because they did not have adequate mass. So at different steps, when the fusion reaction stops, we have different kind of stellar remnant. So for example, if this is the main sequence mass, this scale shows the main sequence mass, from 0.08, that's the lowest mass of a gaseous blob which would become a star, 0.08 solar mass to 8 solar mass. A star goes into main sequence, then a red giant phase, then a planetary nebula, and ends up as a white dwarf. Similarly, an object with a mass of 8 to 25 times the mass of the sun, would end as a supernova and then go into a neutron star. For objects with masses larger than 25 solar mass, the objects will end up as black holes. Now, we would deal with objects which have gone as neutron stars after going through the phase of a supernova. Now, what are the dimensions of a neutron star when it is formed? The mass is about 1 to 3 solar mass. The maximum mass so far observed of a neutron star, that is measured from indirect quantities, is 2.14 solar mass, that is known so far. So therefore, the mass of a neutron star is about 10 to the power 33 grams, and the radius is 10 to the power 15 kilometers. So this is an extremely compact structure, a solar mass object bound inside a dimension of a small city, smaller than Pune. So this compact structure has several consequences. What is the consequence? The first is the binding energy. So if you estimate the binding energy of such an object, that comes out to be 10 to the power 53 arc. And we had said in the context of Buddy and Zwicky's work, then they looked at the amount of energy being put out by a supernova, and from that they suggested that a compact object must be created at such an event because this number comes from the binding energy of such a compact object. And then if you look at the Schwarzschild factor for such an object, you end up with a number which is rather close to 1. So therefore, general relativistic effects would be important if you are discussing the physics of an object near neutron star. Once again, this compact structure gives rise to very fast rotation. Now, the minimum spin period that an object can have, that is the if an object is very compact, it can rotate very faster and its spin period becomes very small. So the minimum spin period of a gravitationally bound object is given by this formula, which you can calculate easily. Now, this number is about 5 into 10 to the power minus 4 second for a neutron star, that is half a millisecond. So half a millisecond is the spin period that a neutron star can have. Now compare this number with the number for Earth. The minimum spin period that Earth can have is 1.5 hours. So it's way larger. Okay. And what have we discovered so far? The minimum spin period that we have seen of a neutron star is about 1.4 millisecond for this object. This is the telephone number of that particular pulsar. PSR stands for pulsar. And I said that the minimum spin period that a neutron star can have is about half a millisecond. So what we have seen is 3 times that number. So of course, we are seeing objects which are very close to the minimum limit of the spin period. So neutron stars, because they're very compact, they can spin very fast, and that has many consequences which we will talk about later. Also, the central density of such an object is extremely large. Now, if we consider the magnetic field pressure, which is comparable to that kind of central pressure. Why do we want to do that? Because if an object has to sustain a magnetic field, now please remember that the 2 characteristic properties of any astrophysical object, which gives its many other interesting properties, are its rotation and its magnetic field. So rotation and magnetic field, and they are in some way they are connected to each other. So rotation and magnetic field are the 2 most important properties that one needs to consider for an astrophysical object, and in particular for neutron star, these are extremely important. So now, if an object has to sustain a magnetic field, then the material strength should be such that such a strong magnetic field can be supported by that material. So therefore, one needs to look at the pressure that a magnetic field would exert on a body and see whether the material pressure is large enough to withstand the electromagnetic pressure exerted by the magnetic field. So if we compare these two numbers, we get the maximum field sustainable for a neutron star is about 10 to the power 18 Gauss at the center. And the maximum magnetic field that we have seen so far in a pulsar is about 10 to the power 15 Gauss. But one has to remember that we are seeing the field at the surface. So at the center, it might be a little stronger. But these are the kind of numbers that we are dealing with. And please remember that low vulture, even before neutron stars were discovered for the first time, from basic physical considerations, from the flux conservation of stars, which will go into neutron stars, gave similar kind of numbers. Low vulture said the magnetic field should be around 10 to the power 14 to 10 to the power 16 Gauss, and we are getting similar numbers here. So here you have an object which behaves very close to what our theoretical expectations are. So this is very interesting. This is a completely exotic object sitting in the sky, and we have no way of looking at it directly, and it follows our theoretical predictions. So that tells you the power of theoretical understanding. So here is a comparison chart for magnetic field of various astrophysical objects, starting from Earth to Jupiter, brown dwarf, sun, white dwarf, and neutron stars. Please look at the last two columns. So this column, the third column, gives you the magnetic field observed at the surface. And the fourth column gives you the maximum magnetic field that the object can have at its center. So you will see that except for these last two objects, the white dwarf and neutron star, the surface magnetic field is way smaller than the maximum magnetic field that it can have at the center. When you come to white dwarfs and neutron stars, the surface fields are actually only 1,000th of the maximum field that it can have at the center. So therefore, at the center, it may have magnetic field which is very close to the maximum limit. And you know from basic physics considerations, when any physical characteristic is very close to its limit, either minimum limit or maximum limit, it behaves in a very ideal fashion. And that is the reason why neutron star physics, even though very complex, is so close to our theoretical predictions. Now, some more consequences of the extreme physics is that because of this mass and very small radius, we have the average density of the neutron stars between 10 to the power 14 to 10 to the power 15 grams per cc. And you know that the nuclear density is 2.3 into 10 to the power 14 grams per cc. So therefore, this entire object, this 10 to 15 kilometer object, this is at a density of an atomic nucleus. Now remember what Landau said in 1931. It's like a giant atomic nuclei in the sky. And neutron stars are exactly that. They're giant atomic nuclei in the sky. Because of this high density, we have certain considerations coming from the statistical property of the particles there. Now, even though it's like a giant, it's like an atomic nuclei, the number of particles is huge. In an atomic nuclei, even in the very heavy nuclei of uranium, we have something like 234 to 35 particles. But in a neutron star, we are talking about an atomic nuclei in which you have particles of the order of 10 to the power 39. So that many particles, they have their very specific statistical behavior. The material is degenerate in a statistical sense. So electrons are relativistically degenerate, protons are non-relativistic degenerate, and neutrons are non-relativistically degenerate. Now we are talking about neutron stars, and you would say that where are the protons and electrons coming from? Uh, a neutron star is, though it's made up of 90% neutrons, but there are 10% protons and adequate number of electrons to keep it charge neutral. This high density also ensures that we can deal with the system as a zero temperature system in a statistical sense. So therefore, this huge atomic nuclei, which may have a temperature of 10 to the power 9 Kelvin at birth, and then later on ordinary cold neutron stars have a surface temperature of 10 to the power 6 Kelvin, but we can deal with it as if it's a zero temperature system, because the Fermi temperature of the system is much higher than these temperatures that are usually realized in neutron stars. So now let us go into understanding the emission behavior, why a neutron star behaves like a radio pulsar. So what we see from the sky is a periodic set of pulses, like you see on your screen, which is observed by radio telescopes like GMRT, that is maintained by National Center for Radio Astrophysics, TIFR, here in Pune. So what you see are these extremely regular periodic pulses. Now, how does a neutron star emit such pulses, and why does it do it? That is the basic question. What we see from various neutron stars is that we have different kinds of shapes of these pulses. Sometimes you see that a pulse has small little features in the pulse. Sometimes you would see that there are two pulses that appear, two separate pulses that appear one after another. Sometimes there are not two sharp pulses like this, but behave like this. Sometimes a pulsar may have different kind of pulses at different times, and so on. So wide variation in pulse shapes and sizes, and also different shape at different times. So this is in radio. But do the neutron stars, do the pulsars emit only in radio? No, certainly not. They also emit in higher energies, and this is a combined picture of various pulsars emitting at different wavelengths. You will see that this is gamma ray, X-ray, optical, and radio. You see that the nature of the pulse, the shape of the pulse, it's very different from energy to energy. And sometimes, for example, in this case, and in this case, and this case, you may not have a pulsed behavior for various energy bands. So a particular pulsar may not emit in all the energy bands that we are looking at, but there are pulsars, notably CRAB. CRAB is a very interesting pulsar because CRAB as an individual pulsar gives us the maximum amount of information on neutron stars. It has all sorts of phenomena associated with it, and it also emits in all the wavelengths. So CRAB is very important for pulsar physicists, but you see that this pulsed behavior is the same in different energy bands, though the shape of the pulse might be very different. So what is giving rise to these pulses? So this is a typical pulsar geometry. You have the neutron star here, and let us assume it has a dipolar magnetic field. So that is the axis of the magnetic field, and there is a dipolar magnetic field, and it is rotating, as I have already said, It's rotating very fast, but the rotation axis is not aligned with the magnetic axis. So the rotation axis is at an angle with the magnetic axis. What does that do? There are charged particles which are streaming out of the neutron star because it's a magnet which is rotating with an angle to the magnetic field axis. So therefore, the magnetic, with respect to the rotational axis, the magnetic field is changing over time, and a time variable magnetic field gives rise to an electric field, an electric potential, which is responsible for generating charged particles in this region, the immediate vicinity of a neutron star that is full of charged particles, and we call it the magnetosphere. So these charged particles are moving along the field lines of the magnetic field, and when charged particles move along magnetic field lines, they give rise to radiation, and that radiation is seen by us in radio, in X-ray, optical, etc. So now what happens is when the charged particles are giving rise to radiation, this radiation, this open field lines are the lines along which the charged particles are moving and the radiation is coming to us. And obviously, this creates a cone. These open field lines is like a pencil beam, a fan-shaped radiation pattern. Now, because it is rotating, this radiation beam hits our line of sight once every spin period, and that's when we see a pulse. Now, you would ask, why these open field lines? What is open field lines? Now, this is called a light cylinder. This is an imaginary surface near the neutron star. A neutron star is rotating at a particular spin period, and if you have a magnetic field stuck to the neutron star, that is also rotating along with the magnetic field, along with the neutron star. Now, as you go further away from the neutron star, there comes a point, a radius r, at which r omega, where omega is the spin angular, where omega is the spin period, spin frequency of the neutron star, when r omega equals the velocity of light. So beyond that point, the magnetic field lines cannot co-rotate with the neutron star, and those constitute the open field lines. Now, the magnetic field lines which co-rotate with the neutron star are called the closed field lines. They co-rotate with the neutron star. Now, beyond this, particles can stream along these open field lines, giving rise to radiation, which is what is observed as neutron star or pulsar radiation that we observe through our telescopes. Now, this magnetosphere is field dominated. What does that mean? That the gravitational energy of a particular particle is much, much smaller compared to the electromagnetic energy of a particle. If you compare the forces between the gravitational energy and the electromagnetic energy on, let us say, an electron, then the gravitational force on an electron is much weaker compared to the electromagnetic force on an electron. So therefore, the movement of an electron is completely determined by the electromagnetic consideration rather than the strong gravitational force that is being exerted by the neutron star. So in the magnetosphere, the movement or the behavior of charged particles is completely determined by the electromagnetic consideration. The magnetosphere is also force free, I'm sorry, and therefore that determines the net charge density in the magnetosphere, and therefore that determines the various properties of the emission. Now we talked about brightness temperature of an emitting region. Now what is a brightness temperature? You get an intensity of some radiation observed by a particular telescope in whichever frequency band, and you say that let me assume this radiation is a black body radiation. So therefore, if you compare the intensity at a particular frequency nu to its black body spectrum, you compare this, you equate this to the Planck function, that is the black body radiation, and you get a temperature. Now that temperature is known as the brightness temperature of an emitting region. So how do we do that? We use, if we are in the Rayleigh-Jeans regime, where the energy of a particular photon given by h nu is much less than kBT, where T is the black body temperature. We are in the Rayleigh-Jeans regime of black body. From this equation, we can find the black body temperature of any emitting source in the sky or any terrestrial source, whatever you have. Now, if you consider the pulsar radiation, where the intensity is about 10 to the power 4 to about 10 to the power 7 in arcs per second per centimeter square per hertz per steradian. That is the CGS unit of intensity. What we obtain is the brightness temperature is obtained as 10 to the power 23 to 10 to the power 26 Kelvin. Now, clearly, that's an absurdly high black body temperature. No physical system can sustain this kind of temperature. This will give rise to unphysical particle energies, and of course the emission would be at a much higher frequency range, not in radio. So a radio emission having a brightness temperature of this is simply telling you your equation is wrong. Not the black body temperature is black body equation is not wrong. What you're saying is you are using the wrong equation. So this is not a black body radiation, but it must be some other mechanism that is coherently giving this kind of an impression of such a high black body temperature. This is not a black body radiation. So what we have now come to understand is that the radiation of a radio pulsar, a neutron star, can be given by a dipolar model, as I have said before. So you assume that it's a dipolar magnetic field, then you can define the stellar magnetic moment in terms of its angular inclination from the radiation axis, the surface dipolar magnetic field, the stellar radiation, the stellar spin frequency, and so on. And you can calculate what would be the energy emitted by this particular object. So this is called a rotating dipole model. Now, rotating dipolar model, if you work out the formulae, what you obtain is the energy radiated dE dt, that is the change in the energy per unit time, is proportional to the square of the surface magnetic field. And fourth power of the angular frequency. Now the rotational energy, how do we know that what is the source of the energy that is coming to us? Now that energy, the radiation, is coming at the expense of the rotational energy of a neutron star. Now the change in the rotational energy would show up as a change in the spin frequency. So change in the rotational energy is given by I omega dot, where I is the moment of inertia of the neutron star. So now if you say that this radiative energy is coming totally at the expense of the rotational energy, and you equate these two quantities, this top quantity and the bottom quantity, then what you have is the surface magnetic field is given by, there are some constants which have been converted into numbers. So basically this is given in terms of the spin period, that is PS, and the spin period derivative. You remember that the spin period is changing because the radiation energy is coming at the expense of the rotational energy. So the surface magnetic field is now given in terms of the spin period and spin period derivative. So here is an object which is giving away some radiation. We look at the radiation, we calculate its spin period. Spin period is easy to calculate because the pulses are coming at an interval of the spin period time. So we calculate the spin period, look at the change in the spin period, and what we have in the end is an estimate for the magnetic field. So this is using basic physics to get at some characteristic property of this object, which would not be easy to obtain. And this also gives us some estimate for the characteristic age of the pulsar. So we assume that it started with a very short spin, and then it has arrived at the spin of today with this kind of spin period derivative. So therefore that gives us a characteristic age. So measuring the spin period and the spin period derivative has given us the characteristic age of the neutron star and also its characteristic surface dipolar magnetic field. So in summary, the radio pulsar model has used the fast rotation and strong magnetic field of a neutron star to understand that there will be strong electric field which would accelerate charged particles, and radiation would come from these charged particles. There will be pair productions and the free charges streaming along the open field lines, and the radiation processes would be synchrotron radiation, Compton scattering, curvature radiation, and so on, which will give us the pulsar radiation in various frequencies. The spin period measured of neutron stars, I have already said that there are about 3000 neutron stars which we have observed so far. So spin period measures from about a millisecond to about close to 100 seconds or so. Surface magnetic field ranges from 10 to the power 8 to 10 to the power 15 Gauss, and we sort of understand the pulsar radiation through a dipole model. Now, the slowdown could also have other factors that are responsible for it. We understand that there would be gravitational radiation at the cost of rotational energy. Let us not go into the details of that. I would only say that for the electromagnetic radiation, the change in the energy was proportional to omega to the power 4. In case of gravitational radiation, that would be omega to the power 6. So that would give a completely different characteristic age if the energy loss was entirely due to gravitation. We know which is not, because there is this strong electromagnetic radiation that is coming out, and the actual slowdown is a combination of electromagnetic and gravitational radiation. So the neutron stars slow down by a power law. So what we mean by a power law deceleration is this, that omega dot is proportional to omega to the power n, and n is therefore can be obtained from this formula. So n is called a breaking index. N equal to 3 for magnetic dipole radiation and n equal to 5 for gravitational radiation. N is equal to 3.43 for Xray Pulsar. There are various combination effects in that, but n is usually much smaller for many pulsars, and we really do not know what gives rise to all these different kind of breaking index. So that is one piece of physics not really understood, and many people are working on that. Now we come to the point where we would talk about timing and null. Now this is one piece of physics that is not yet understood, and we are trying to, many people are trying to look into the phenomenon of null. Now, what is null? Let us look into that. Before that, I have to tell you that when I say that a pulsar has a spin period of 1.3 millisecond and so on, you have to understand that the measurement of the period is very, very precise. And also the spin period derivative, that is also very, very small. Otherwise, such a small period would change if we had a large derivative of the spin period. So here are some numbers. So the spin period derivative P naught, that ranges from 10 to the power minus 22 to 10 to the power minus 10 second per second. So therefore you see, even over the Hubble time, the change in the period would not be significant. So what is said, here is a plot of this quantity sigma z is a fractional stability of clock quantity that is used by clockmakers over time scales. And this solid line is for atomic clocks, and these other lines are for millisecond pulsars. Millisecond pulsars are pulsars which have a spin period of order of millisecond. Now they seem to be very stable, even more stable than atomic clock over long period of time. So therefore, in order to measure the spin period and the spin period derivative, our measurements must also be very, very precise. We would skip this. Okay, let me mention that. So therefore, since the pulsar clock is very, very stable, we can use pulsar clocks to measure something else. For example, we can use a grid of such pulsars to measure the propagation of very low frequency gravitational waves. Such gravitational waves would be very difficult to measure with our earth-based detectors. So there is an effort to make PTAs, pulsar timing arrays. So we have detectors for gravitational waves in the sky. Is a number of millisecond pulsars in the sky. We know their position, and we use them to detect gravitational waves passing through that region of space. And how that is done is a complicated piece of physics. I would not go into that, but there are many pulsar timing array efforts that are going on all over the world. And we also have an Indian pulsar timing array, which is part of this work. And many Indian scientists are involved in this work. skip that. So now when we look at pulsar pulses, we also have to measure whether it is coming precisely at the time that it should, or there is a change in its arrival time. Why do we need to do that? Because that is what would allow us to calculate the period derivative. So what we call TOA, that is the time of arrival, that needs to be very precisely defined. So one pulse arrives, and when the next pulse should arrive, when would be its time of arrival, TOA, that should be very precisely estimated in order to find whether there has been a change in the period. There are certain sudden changes in the period, which is called glitch. We will talk about glitch in the next week's lecture. So therefore, we must know very well what should the TOA be for the next pulse to arrive. Once I have a pulse, when should the next pulse arrive? So here is a schematic diagram as to how this TOA is calculated. You have, there is this neutron star, and it's detected by a telescope. So there is a telescope receiver. It does de-dispersion. It's an electromagnetic wave moving through the interstellar medium and the ionosphere. All these places have charged particles, and the pulse gets dispersed. You know what is dispersion, and so all that needs to be taken care of, and mean pulse to be generated. Now there is a reference clock with which we compare and find what should be its time of arrival. Now the time of arrival has various delays intrinsic to it. So and there are models through which this can be found. I would not go into the details of that, but just to give you a glimpse of that, there could be many types of delays of a pulse arrival. There could be solar system barycentric delay because we are at a particular place in the observatory. Now, this observatory is moving along with the Earth around the sun. So therefore, our position is moving. So that gives us to certain delays. There are various clock corrections. There are corrections for dispersion measures. And there are various other kinds of delays. For example, correction for space-time of the curvature, corrections for gravitational redshift when it moves past a massive object. And this is all for isolated pulsar. If it is a binary pulsar in the sense that it has a companion, then the orbital movement itself would give rise to some other delays. All that has to be taken care of in order to understand how to correct for the time of arrival. So now after we have done all that, this is what we finally do. There is a radio pulsar. Ideally, this is what we should be looking at. Very stable, steady, regular pulse. But all pulsars do not behave like that. There are certain pulsars, for example, this one, the second one called a nulling pulsar. Some of the pulses disappear, just disappear. We do not know why, but some of the pulses disappear and then they come back and go on as usual, but some of the pulses in the middle are lost. Then there are situations where we have extreme nulling. They are mostly not there, mostly not doing anything, but once in a while they appear, have regular pulses, and then they disappear again. And then we have RRATs, rotating radio transients. Why transients? Once in a while they come up, throw a pulse, and then they disappear again. Okay, so there are all these behaviors which we do not understand very well. If you look at the pulses, this is a different way of looking at pulses. You see that all these black dots, these are the pulses, and these gaps in between, these are the absence of pulses. So this is one pulsar, this is another, and you see that the nature of the disappearance of pulses is also very different. Here the pulses disappear reasonably after a short time. Here the pulses disappear for more time than they are there. Here the pulses disappear only for very short amount of time. And this fellow has only one pulse in this span, and most of the time it was absent. Okay, so there are various different kind of nulling patterns. We would skip these. Now, the pulsars also sometimes change their nature when they are nulling. So sometimes when it is nulling, the radio bright, it's brighter in the radio and dim in X-ray, and vice versa. So such behavior is also seen. Sometimes the nulling phase also throws up a different kind of pulse profile. See, for example, particularly look at this one. When it is, it has this regular pulse. After a null, it has this peculiar kind of pulse. So nulling changes the behavior of a pulsar. So what is null? Null is abrupt cessation of pulsed emission, and there are various association with drifting subpulses. If a pulse has smaller subpulses associated with it, so these subpulses move differently when there is nulling. And as I have said, there will be mode changes. They also change emission frequency. So within the radio frequency range, the emission may change from one set of radio frequency to a slightly different radio frequency. Sometimes nulling is associated also with the change in the period derivative. That's why I was talking about the time of precise measurement of the time of arrival so much, because there can be change in the spin period derivative, and unless we measure the time of arrivals very precisely, you would miss all this physics. So the characteristic of these nulling pulsars, are all pulsars nulling? No, certainly not. Only about 10% of the radio pulsars, actually a little less than the radio pulsars are nulling. And the spin periods are reasonably large, half a second to about 10 seconds. Magnetic fields are also slightly larger, and they are reasonably old. And this dispersion measure, this DM stands for dispersion measure, which is a measure of the distance of these objects, doesn't tell you anything, because these nulling pulsars can be nearby or far away. So basically they are slightly slow pulsars, and slightly magnetic field is slightly higher on the higher side, and they're slightly older. Now, we define a quantity called a nulling fraction. So nulling fraction is how much time it's in a nulling state. So this could be, for certain pulsars, it's even 95%. So 95% time they are not there. They're just sitting quietly. Now, there is one quantity that many of us would like to have a handle on, is the null length. For how long it disappears, and then after that it comes back. Now, there is not much data, and because it is very difficult to estimate the length of a nulling phase, and therefore there is not much data on that. And but that would be an important quantity that we still do not have. And but based on the pattern that you have already seen in the pictures, is that we have different kind of nullers. The classical nullers, only a few pulses go missing, and then they come back, and then again a few pulses go missing. The intermediate nuller, they disappear for many pulses, up to few hours. So as you can guess, if the spin period is about a second or so, if they disappear for a few hours, that means they are absent for thousands of spin periods. Then there are intermittent pulsars. They disappear even for years and then they come back. And I have already talked about the RRATs, so which are characterized by single pulse emission. So there are different classes of nullars. So are they all the same, or are they manifestation of similar physics in different variation? We really do not have a unified theory for nulling pulsars, and that is why this is a very interesting challenge for a theoretical person like me. So I would like to understand from the data that is available. Now I am talking about the archival data. So this data is available to us, and we haven't understood why we have nulling or whether it is associated with something. There have been some suggestions very early on which said that the nulling pulsars are actually uh, an indicator of old age. What is old age? Now, the neutron stars act as pulsars because they have strong magnetic field and they have very fast rotation. Now, we have already seen that they slow down. That means the spin period becomes longer and longer. The frequency becomes smaller. Now, there comes a time when the combination of the magnetic field and spin period is such that the electric field generated, this combination generates the electric field, which is actually responsible for having the radiation from the neutron star. So the combination becomes such that the electric field is not strong enough for the charged particle production in the magnetosphere of the neutron star. And that is the time when a neutron star stops behaving like a radio pulsar. The neutron star is there, it's spinning, it has a magnetic field, but the spin period and magnetic field combination is not suitable for charged particle production and therefore pulsar radiation. Now that is called a pulsar death, and this is given by certain assumptions about the emission process, and a death line is calculated. What is a death line? It is a formula which gives you the combination of spin period and magnetic field beyond which a neutron star is not able to function as a radio pulsar. So this is a plot of known radio pulsars in the magnetic field spin period diagram. In the y-axis, you have magnetic field. In the x-axis, you have spin period, and blue dots are all known radio pulsars. Now you see the blue lines, blue dashed lines on these plot. These are death lines. That is, on the right hand side of these death lines, the neutron stars would not function as radio pulsars. Now these different death lines are obtained by assuming different physics. Now, for example, the death line number 2 is calculated when the magnetic field is extremely curved. On the other hand, death lines 5A and 5B are calculated for a central or slightly shifted from the center, body-centered dipole, a pure dipolar magnetic field. Now, the red circles are the nulling pulsars, and you notice that these red circles are somewhat limited by the death line, which is number 2. So then one says that, okay, so maybe all the nulling pulsars have very curved fields, and they are about to sort of die off, and that's why they are uh, nulling. So that is one, that could be one suggestion. So now we have suggested that that is a possibility in the article that I have referred to here. And so then the next question becomes, if that is really so, we should be looking at all the other pulsars which are also nearby to this death line, whether they are nulling or not. Okay, so you may say that there are many pulsars in this region which are not nulling. So is such a suggestion sensible to say that all the nulling pulsars are very close to death lines, they're about to die off, and therefore they are nulling? The point is, when a radio pulsar is observed for the first time, now that we have a large number of radio pulsars which are being detected almost every day, unless and until there is something very interesting about a particular pulsar, we do not go and observe it carefully. So there are many pulsars which are detected, and we know about their spin and the spin period derivative, but we do not know about their long-term behavior. So there might be a large number of neutron stars, radio pulsars in that region which are also nulling, which you do not know about. So then the task becomes to go and look at those objects to find if they are nulling or not. Currently, we have proposed a geometry project. Our proposal has been accepted, and our observation is going on. And this is exactly what we are doing. We are looking at all these blue dots here, these bluish gray dots here, which we do not know about whether they are nulling or not. We are looking at many of them to see whether they are nulling or not. And the preliminary result is very, very encouraging, so to speak. But the point is, so you get to a new direction in your investigation when you look at the existing data and figure out that what would be the direction in which this research should go. Now that we are looking at the GMRT, we are currently observing with GMRT, that is a project in which we would be taking data and looking at it directly. But the work that has gone into this paper has been based on archival data, and which has prompted to this new GMRT project. But that's a later part. So this, what have we done with archival data? There were many investigations into various pulsars, and people reported existence of nulling in various pulsars. But there were no large repository where one can go and check up, okay, these are the pulsars that are nulling, and therefore let me look at the characteristic of this population. So what we did, we trawled through the literature. We went basically individually, paper by paper. We extracted the information for all the nulling pulsars that were available. We made our own archive of nulling pulsars, using which we could do this work, which prompted us into this next GMRT project. So therefore, this is one example as to how different kind of archival data can lead you to a interesting investigative project. So in the course of this lecture series, I would talk about, and as a project, I would urge you to work on that. People who would be interested in taking up that project, we would try to find an evolutionary pathway between one type of radio pulsars and another type of radio pulsars. I'll talk about those later. But this example I wanted to give you in order to tell you how different kind of archival data you can imagine, and how this kind of archival data would lead you to different kind of projects. So I see that it's already 11:30, and I wanted to show you a bit about the repositories. So I'll just go to the repositories. This my PDF file of the presentation would be available, as Priya tells me, and so you can check out the repository websites later on. And instead of doing that, I would probably take up the questions that you may have put in the chat box. So very quickly, these are the resources. Please look at the books a little bit, whatever you can access. The first book is very important for people who are, I really do not know the level of people who are taking this, listening to this lecture series. So that's at a much lower level than the books after those. But please take a look and see whatever is suitable to your level, and how much you can grasp from them. These are the databases for various avatars of neutron stars, the radio pulsars, Xray pulsars, magnetars, and so on and so forth. And the ATNF is the main repository for all characteristic parameters of all the observed radio pulsars. Please go to this ATNF site. Please play with the site and try to check if you can handle sort of inquiry from that site. The huge amount of data can be found from this site, and then there are other sites from which we can get various other kinds of data. So I would leave it to you to go into this in particular the ATNF database, the first one, and play around with it, so that when we get into the project, you know how to handle these databases. And now I would check up the chat box and see if you have any questions.
Yes. Yeah, so,
There are some questions there.
hi, Sushan.
Yeah.
Thanks
Hi.
for that lovely talk.
Thank you very much. So
I think you can see it, right? The first one is with RR80.
I cannot. There is the chat box. Yeah. Okay, now I can see it. Okay, so a lot of happy Teachers Day. Thank you very much. RR80 characterized by single emission. Do you mean a single emission in their whole lifetime? No, certainly not. Then we would not know what they are at all. Okay, so what they do is they have single emission, and then they disappear for an arbitrary amount of time. Then they come back, and then again disappear from an arbitrary amount of time. So then you would say that how do we know what is the period of such an object, the spin period, etc. So that is a very difficult proposition, and in many cases, period has not been really found. What one does is, for an RRAT, if you have a number of single emission pulses, so you take the time difference between two consecutive emission pulses and try to find the greatest common factor between these intervals, and that is sort of that sort of hides the actual period. So the kind of the lowest common denominator of the intermediate times, that gives you the period of the RRAT. Okay, so yeah, it's very difficult, and it's very complicated, and that's the reason why we do not have all the characteristics of RRATs. But no, certainly not only one single emission and then they disappear. Okay. Why are the peaks of the same shape? The peaks, no, the peaks are not of the same shape. They look similar, but if you look at the details, no, they look very different in from pulsar to pulsar, from for the same pulsar from frequency band to frequency band. They look very different. For the same pulsar in different frequency band, they may look a little similar, but they may not. So no, they may look similar, but they are actually very different. There's wide variety. Does the magnetic field has an effect on the energy distribution profile? Sometimes we feel that when the pulse shape is very complicated, the magnetic field has a much more complicated structure than the simple dipole that we assume. We assume a dipole because it's the simplest to work with, and we know the equations and we can easily handle them. But it has been shown, in particular by a colleague of myself, Dipanjan Mitra, that the magnetic field may have very strong multipoles near the surface and very complicated structure. Yeah, sometimes they show up in the let me rephrase. Sometimes we understand how the magnetic field structure is showing up in the pulse profile, but in most cases we do not really know how to translate the pulse structure to the magnetic field profile. Yes. Can glitches in millisecond pulsars? Yes, glitches in millisecond pulsars can affect nanohertz gravitational wave observations, and therefore, first of all, millisecond pulsars are used for pulsar timing arrays because they are very stable, and also because barring two millisecond pulsars, none of them show glitches. Only 2 millisecond pulsars have shown glitches, and obviously they would be excluded from such timing arrays. Yeah. How is the magnetic field generated inside a neutron star? That's a very important and interesting question, and let me say that we still do not have the we still do not really understand it, but I will talk about it either in next lecture or the lecture after that. Yeah. Do all radio pulsars? No. All radio pulsars are not 1.33 second. As I said, they vary from about 1.4 millisecond to about 10-15 seconds. So there's a huge range. Oh, I missed a question there. Time lag properties. I don't think I understand the question. Okay, I will come back to that. In stellar graveyard plot, we do not yet observe any candidates between mass range 3 to 5 solar mass. Stellar graveyard plot, you mean? Okay, let me go back to the plot and see. Okay, let me share the screen a little bit. So if you are talking about this plot, I'm assuming you are talking about this plot. There is no gap between 3 and 5. I do not see 3 to 5 solar masses. 3 to 5 solar masses is here. It's in this first bunch itself. So from 0.08 solar mass, that's the lower mass limit of a star, to about 8 solar mass, all go into white dwarfs. But please remember, these numbers are not very strict numbers. The number 8 or 25, these numbers are not very strict, because they depend on the composition, in the sense that whether the starting material is mostly hydrogen, or there is a little bit of helium and heavy metal. In astrophysics, everything heavier than helium is metal, so there is contamination of those materials. So it depends on the composition a little bit. So 3 to 5 solar mass is very much within the white dwarf range. You said that we are trying to figure out an evolutionary pathway, all types of pulses. Okay, the last question is is very interesting. Yes, we would talk about the evolutionary pathways in the last lecture, and that would be part of the project that we'll be trying to define. Yes, there are some people who say that no, there are these different flavors of neutron stars that they are born with, and why should we worry about whether there are evolutionary pathways or not? Yes, but you look at certain associations between a particular type of neutron star and their environment and their various properties, and then you look at another type of neutron stars and their environment and properties, and etc. And there are reasons when you believe that this set probably have evolved into this set because they had certain environmental conditions or something else. And then such a theory remains a theory as long as you do not see a missing link between them. And many times you see the missing link. And let me tell you that I worked on such an evolutionary pathway during my PhD. And I think a few months after I submitted my thesis, a missing link was discovered. So therefore, that is kind of a vindication of all that you do. And the kind of project that I have been trying to define when I first talked to Professor Priya Hassan is that a missing link has just been announced yesterday. In yesterday's Astro PH, there was a talk of a missing link. So that's what tells you that some objects transition from this population to that population through an evolutionary process. Yes. What is the characteristic of nulling? Is it an intrinsic? What is the characteristic of nulling? No. What is an extrinsic property? You mean that we somehow do not see them? No, that has been talked about by some people, and there are enough indication to say that it's an intrinsic property. And what is it? That's what we are trying to understand. We still do not know. We have Chandrasekhar limit for white dwarf. Do we have some kind of limits for? We have some kind of limit for neutron star. That also depends on the composition a little bit. And the equation of state, by equation of state, I mean what kind of material is actually there inside the neutron star. When I say it's all neutrons, protons and electrons, that is not what it is. As you go to very high densities, 3 to 4 times the nuclear densities, there are exotic particles, could be quark matter, could be hyperons, etc. Such exotic particles would show up in the center of the neutron star. And that physics, as I said, because it's not possible to investigate such material in the terrestrial laboratories, our understanding of such material is not sort of 100%. So we have to depend on extrapolation of our current knowledge and say that this is possible, and probably that kind of thing is also possible. So there is uncertainty in trying to understand what exactly happens in the extremely high density regions of a neutron star, and therefore the mass limit, the maximum mass for neutron star depend on that. And black holes, of course, black holes do not have any mass limit. That's when gravity overcomes all that matter can throw at it, all kinds of processes that can support the gravitational pressure. When everything fails, then we have a black hole. So no, there is no mass limit for black holes. Yeah, I think that's what it is.
There's one more question.
Has any EOS theoretically predicted nulling? No. This has not. There hasn't been any connection with nulling to EOS.
Yeah.
Maybe Subhashish, what he asked, time lag properties is there. Probably they're saying, does time lag, do they have properties? Time lag?
Yeah, that
probably
that
that's what it is.
question that question we skipped. Yeah, I probably haven't understood the question. If the person who
Yeah.
has written this can explain a little.
Subhashish, you can retype or unmute yourself. Okay. Yeah. So Subhashish, you can unmute yourself or you can retype your question. Are you there? You're there, right? Hello, Subhashish. Okay. Okay, there's another question from someone else, from Shams Hussain. Madam, why don't all supernova remnants contain
Okay, this pertains to details of stellar evolution physics. So different stars have different final stages, and the Loma stars, there are different types of supernova actually, depending on the original star that has gone supernova. And it's only one kind of supernova, that is supernova type 2, that gives rise to neutron stars, not all types of supernova. So that has to deal with details of stellar evolution physics.
Yeah, I think that's it. This guy has not written his question. Probably he can do it next time. He can, Subhashish, you can rephrase your question better.
He does. Time lag means soft or hard lag.
What's the soft or hard lag?
I do not think this is relevant in this context. I suppose you are talking about maybe X-ray observation in which they have.
Hello.
Yeah, please.
Sorry, ma'am.
Yeah.
So sometime you tell that the radio pulses are behave like as an X-ray.
No, radio pulsars do not behave like X-rays. What I meant is that you have a neutron star which is acting as a pulsar, and this radiation, when it acts like a pulsar, this radiation may come in different kind of wave bands. So the same object may radiate in radio and optical and X-ray and gamma ray, but the same object may not radiate in all wave bands. So some radiate in all wave bands and some do not radiate in all wave bands. Okay, so there is no lag between them.
Okay, do you think he meant lag in the frequencies for different emissions? What for radio, X-ray, etc.? Okay, there's another question. No.
Okay, 250. No, that has to do with whether it becomes a star itself, not a limit for stellar black hole. If you see that the evolution of stars, evolution of massive stars, go through very complicated phases. Particularly if massive stars are in binaries, they lose masses, they transfer masses, and all sorts of things happen. So there is no physical limit to the mass of a black hole, and putting a mass from the stellar evolution scenario is also not very appropriate, because there could be mergers. So then the merger would jack up the mass of the black hole. So one does not try to put a mass limit on black holes, so let us say.
Yeah, so I don't see any more questions. And yeah, so I think we can wind up our session. Thanks a lot, Sushan. This was really fun,
Thank
and
you.
there are lots of questions over here. But we have 3 more Saturdays with Sushan, so there'll be even more questions hopefully then. Sushan, just for your information, these are UG,
Yeah.
PG students with
Okay.
science, physics, math background, as well as we've even permitted BTechs. So there are
All
BTechs
right.
also in there. And so I guess some basic physics math they should be able to handle. That was this thing. Yeah.
Okay.
So thanks a lot, Sushan. And we'll meet again next Saturday.
Yeah.
And for the students, we'll meet tomorrow morning, and tomorrow morning, 10 o'clock. So we'll meet you there. Yeah. So thanks a lot. Bye bye.
Thank you very much.
Yeah.
Thanks a lot.